Alrighty then, at last. All right, we're going to talk about an RLC circuit. And first we have to assume one thing, that a motor generally is viewed as a resistive and an inductive load. This right here might be how we view a motor. The resistance, the pure DC resistance, and the inductive reactance. And so we're going to look at that, what happens when we take a look at a motor. So a motor can be viewed as a pure resistance and inductance. We have a motor that draws, in this particular case, we're going to say that we have a motor that draws 7.5 amps at 120 volts. Now, if we know that, and we've already taken the resistance of the windings, and the total resistance is 12 ohms, and we've read that with a meter, then we know a couple things. Now, how do I get this over here? Where are my slides? Oh dear. All right, so knowing this, we can use the PEI, EIR wheels to see that to get our total impedance, we would divide the voltage by the current flow to find the total impedance. And we have 120 volts and we have 7.5 amps, so we're going to divide 120 by 7.5, which gives us a total impedance of 16 ohms. Now we took a pure DC resistive measurement on these windings, we found 12 ohms, right? So that tells us our phase angle, does it not? We find from this, if we put in our calculator, second function cosine, what angle has this cosine of 12 divided by 16? It tells us 41.4096 degrees. Where did I lose my... Why does it disappear when that happens? Okay, so since we know our angle is 41.40962211 degrees, we now wish to find the side opposite, the x sub L as it were. We want to find a function that has the angle, one thing we know and one thing we want to know, and in this case that's the sine. And so we know any angle, any function, because we have the angles, we have sine, cosine, and tangent, but we know that the sine has the opposite and the hypotenuse, and we're looking for the opposite, and we have the hypotenuse. So we're going to put in the sine of this angle. So we're just going to punch in sine, second function answer, and that'll give us the sine of this angle, right? Because the last answer we found was the angle, 41 point whatever degrees. And so now we can find, we find our sine of this angle is 0.661437828, and that's equal to O over H. Well, our O is what we're looking for, our side opposite, and our hypotenuse is 16 in this case, right? So all we would have to do is, if we multiply both sides by the hypotenuse will drop out of the right side, right? So if we just multiply 16 times 0.6614 and that whole long number, we'll get the side opposite. So we'll plug that in and we'll find that we have 10.58 ohms of X sub L. That's an inductive reactance that we just inferred from the information we found before, where we have 10.58 ohms. So knowing that we have 10.58 ohms of X sub L, we'd like to get rid of some of that, right? We want to improve its efficiency. And we can do that by adding a capacitor, and we're going to do that, and we know that we don't want to overshoot, so we want to take about 95% of that 10.58, and we multiply that times 10.58 times 0.95, we find that we want about, what is it, 10 ohms? Almost exactly 10 ohms that we want to get rid of, right? So if we want to do that, we need to back into this, and we need to find what capacitor do we need to add to this circuit to get our 10 ohms of X sub C, because it's going to subtract from our X sub L, because they're 180 degrees out of phase from each other, so one just subtracts from the other. So knowing that, we take the formula x sub c is 1 over 2 pi fc, and we know that 2 pi fc is 377. So we're going to say that 10 is equal to 1 over 377 times c. So if we multiply both sides of that by 377, is that the way we do it? Yeah. 3770 is equal to 1 over c. Is that correct? Does 3,770 have a reciprocal? Certainly it does. And the reciprocal of that number is 0.0002652. And if we put that in proper engineering notation, we find that's 265.2 microfarads is what we're looking for. So now let's see what happens here if we do use that approximate 10 ohms. First of all, we find that if we plug in the 265 microfarads, we'll get 377 times 0.000265, and then take the reciprocal of that, and we wind up with 10.009 ohms. Now I want you to notice that the black here is our original inductive reactance. That's from the bottom to the top of the black line. Our x sub c is this red line coming back down here that subtracts our 10.009 ohms, and the resulting leftover x sub L that we're left with is 0.57049 ohms. So our new resultant triangle still has 12 ohms down here, right? Our resistance has not changed. It cannot change, can it? Our capacitor will not affect the resistance of this motor, but we can affect the x sub L, and so we're going to reduce it to a mere 0.57049. So knowing that, previously we had a 41-degree angle, and that had a 75% power factor, right? That meant that it was going to turn only 75% of its incoming apparent power into useful cranking force. Now, is 75% okay with you? Not so much, right? You'd kind of like to have something a little more efficient. Like if your car was getting, if you were paying for, well, I want to get into that, but you can see that you probably don't like 75% efficiency. You're throwing away 25% on just jumping. Remember we talked about the wasting of power by jumping up and down on a pogo stick instead of going forward? Well, we're wasting 25% of our energy jumping up and down on the pogo stick. So we want to change that. Our new triangle has an R of 12 and an x sub L of 0.5707. So to find out our new phase angle, we would use the tangent function, right? So if we do that, we find our new phase angle. We would enter second function tangent. What angle has this tangent? 0.5705 divided by 12, because that's our side opposite and our side adjacent, right? We would find that our new angle is only 2.72 degrees. That's a great phase angle. Taking the cosine of that angle tells us that our new power factor is 0.9987. And that means that 99.98% is going to be turned into real cranking force. Our new efficiency is almost 100%. Which is vastly better. All right, I think that's it for today. And
it's
I take
10
it
o'clock.
recorded. Now, what did I do wrong?